Hi friends, today we are going to see how to multirate a process or how to change the sampling rate by a fractional value. For example, when we do an upsampling or a downsampling, normally we use an integer values. For example, if I have a system which is, let's say it's an upsampler, if I give 8 kilohertz as the input, okay, to obtain let's say 16 kilohertz is nothing but I have to upsample by 2, or I need to upsample by a factor of 2, right? But suppose if I have an 8 kilohertz signal that I need to upsample to, let's say upsample it to, let's say 10.5 kilohertz. Upsampling to 10 is simple. I cannot upsample to 10 because 0.5 sampling rate is been suppressed, or I cannot upsample to 11 because then it will be an oversampling, over than what we are upsampling it, right? So how to achieve, or what should be the system to give us a fractional or a rational value of sampling rate like this? Okay, to achieve that fractional or rational value of sampling rate, we normally use a rational factor or an I by D converter. So we call this as a sampling converter using I by D factor. Okay, so you can have integer i's and integers d, and then when you take its ratio, you are going to get a fractional value or a rational value. Okay, so we will always have an integer I and integer d. Whenever we upsample or downsample, we will always use the integer factors. Okay, in normal upsampler, so I will also always be an integer, d will always be an integer. But if I want a fractional value or a rational value, then I have to actually use a sampling rate converter which is I over D. Okay, now how to do this I over D sampling? It is very simple. In this sampling rate conversion, I will have an interpolator also and a decimator also. Just we need to understand how to connect the system. So I have an interpolator. So I want an interpolator, that means after upsampling I will put a transfer function. Let's say this is a low pass filter, n, we'll write n only. This is my interpolator, okay, and I have a decimator. But then if I draw it like this, it is wrong, because what should be there before this? There should be a filter before this. So I have a filter before this, which is, let's say, downsample. Okay, so I have a decimator and I have an interpolator, and we need to arrange the system such that it will give me a combination sampling rate conversion of I by D. Okay, we know that here if I put fx, then I am going to get here as ifx, which is fy. Okay, here if I give fx, then I am going to get fx by d at the output. Correct? If we multiply these two products, I am going to get I over d fx, isn't it? So if I multiplying in the system is obtained by cascading the system. Correct? So if I will cascade this both the system, then I will form an I over D sampling rate conversion. Okay, so what I am saying that interpolator will give me IFX, decimator is giving me fx by d. So if I multiply this two system, I will get I over D. Okay. So to do this, I will cascade the system because I want multiplication in the process. Multiplication means cascading. So I wanted to cascade these two structures. Now cascading this two structure can be obtained by either doing a cascadation of D and then I, or I can put I and D. So let's say I have to first, we have concluded that we need to cascade interpolator and decimator. Okay, I wanted to cascade this two system. Now cascading can be of two ways. I can put an interpolator first and then a decimator, or I can have a decimator first and then an interpolator, because they will give the same result. Yeah, they will give the same result. You can see, you can check f of x, I f of x, I f of x over d. So I by d f of x, f of x, f of x over d, I f of x over d. They will give the same result. Then which combination we should go about? Should we use the first combination or we should use the second combination? So every time for here to choose the combination, we need to actually understand the basic methodology of what is the spectral analysis or what is the frequency domain analysis of interpolator and decimator. We know that in the interpolator, the spectral quantities or the signal is preserved, because when we upsample, the signal will get just compression. It will not change its shape at all, because we are just having the shape to be compressed in frequency. Okay, so the spectral domain characteristics of the signal is preserved, or the signal characteristics is preserved in the interpolation, whereas the signal characteristics are not preserved in decimation, because whichever frequencies goes above pi over d will be rejected. Okay, so the characteristics in the decimator will never ever be preserved. Okay, so x of n characteristics for the decimator will not be preserved, but interpolation will preserve. So if I use interpolation first, the characteristics of the input will be preserved, and then I will do decimation, then the reconstruction will be more appropriate. If I use decimation first, then the characteristics of the signal, input signal, will be hampered by the filtering process, and therefore the reconstruction will be much more tedious. Okay, so we will always opt for the first scheme, wherein I will have an interpolator first and then the decimator to preserve the input characteristics. Okay, so how to draw the signal, or what will be the block diagram? It will be very simple. I will have an upsampler, and then I will have a upsampling filter. Then I have a downsampling filter, and then a downsampling downsampler. Okay, let us see the frequency or how it works. So it will work like this. Here it is fx, that is my input, x of n fx. Here it is I times of fx. Let's say it has been interpolated by a factor of I, so it is I times of fx. Here it's only filtering, so the rate is not changed, it will be I times of fx again. Here also it is just filtering, so again I of fx, and then it is downsampled by a factor of d, so I times of fx divided by d. Okay, so that is my output y of, let's say, m. Now what we can see over here is I have two filters. Okay, HU of k and HD of k. HU of k is associated with interpolation and HD of k is associated with the decimation. So, and also we can see that both the filters operate at the same sampling frequency, that is IFX. The sampling frequency or the rate of sampling is not changed for any of the filters. So, they are working on the same sampling frequency, as well as one is associated with upsampling, which is an anti-imaging filter or image removal filter, whereas downsampler it is for anti-aliasing filter, or to avoid aliasing we use filtering. Okay, all are working on the same rate. So why not to combine these two and make one low pass filter and see that what will be the characteristics of that one low pass filter. So the compressed version of this is drawn as, we have an upsampler, then I will combine these two filters and I will get one filter which is, let's say, h of k, okay, and then lastly my h of and my down sampler. Okay, this will work at fx, this will work at ifx, output will also be ifx, and then here output will be ifx by d. Okay, correct? There will be same rate, and this is low pass filter. Okay, now once we have done this combination of the filter, I need to now understand what should be the characteristics of this filter, because if you see for HUK, okay, here if I assume that I have two separate filters, then HUK, I cannot have a time domain characteristics, but frequency domain characteristics is HU of, let's say, omega y to be equal to what it should be, equal to I in the pass band, and the pass band will occur, let's say, idealistic situation, not omega y, pi by I, for mod omega less than equal to pi by I and 0 otherwise. Okay, and if I consider HD of omega y, because we both are operating at same factor, so let's say 1, okay, let's say the pass band is unity for mod omega less than equal to pi times of d and is 0 otherwise, pi over d and is 0 otherwise. Okay, so I will now I have to combine and combinedly give a characteristics of h of k, or let's say h of omega y. I have to find what should be the characteristics when I combine HU of k and HD of k and give one h of k. So what should be the characteristics of this combined filter? So the combined filter should provide me the provision of anti-imaging also and anti-aliasing also. Okay, so it should act like an anti-imaging filter also and anti-aliasing filter also. Then how it will operate in both the domain, let us see. So my h of, let's say, omega y, let's say, I say y because it's changing its domain. Okay, omega y, which is equal to I, okay, and is 0, and it will be I for a minimum of pi over I comma pi over d. Now what is this? Minimum of pi over I and pi over d is like this. If suppose I do an upsampling, okay, if I do an upsampling, after upsampling I am going to get compressed version of the signal. I will remove the images and I will check what is the pass band. Okay, if the pass band is not going beyond the limit of pi over d, then this will only act like a imaging anti-imaging filter, because there will not be any aliasing, cause the spectrum is not moving up till pi by d, it is below pi by d, so there will not be any aliasing. That case, low pass filter, this filter will act only for image removals. Okay, but if suppose my after upsampling I got images, I removed the images, okay, now the minimum factor is pi over d, okay, that means the filter is spreaded. Now if I do decimation, there will be aliasing. So what I need to do? I need to in that case there will not be any images, because there is a spreaded signal, okay, spreaded above pi over I. Okay, so what will be happening in that case? This filter, instead of removing images, it will act like a anti-aliasing filter. So when pi by d is minimum, filter will act like a anti-aliasing filter, and when pi by I is minimum, that time this filter will act like an anti-imaging filter. Okay, so I'll write here, I'll write in this case that if I have pi by I as minimum, then h of, let's say, omega y operates as anti-imaging filter, and when pi by d is minimum, the h of omega y operates as, okay, anti-aliasing filter. Okay, and sometime it might act in between them both. If they both are not minimum, in between them both, if it is something like that, then it will act like an anti-imaging and anti-aliasing also, because if you remove the images and if you will provide that compressed version, there will not be any aliasing. Okay, so that is what the filter will act like an anti-imaging or an anti-aliasing filter. Okay, now let us directly go step up to, instead of deriving all the sub points, I will step up directly to the final version, how it will look like. Okay, so we have an, let's say, upsampler, then we have a filter, and finally we have a downsampler. Okay, we are giving input as x of n, we are observing output as y of m. Okay, let's say we create a dummy at this point, which we called as v of n. Okay, and we know that v of n will be equal to x of n into I. Okay, for n taking value as 0 plus minus I plus minus 2i and so on, and is 0 otherwise. Okay, but it will not only be x of n. I am extremely sorry. Let's say v1 of n. v1 of n is over here. Let's say v1 of n. v1 of n is x of ni, because it's only after upsampling. So v of n will be convolution over k goes from minus infinity to plus infinity h of, okay, n minus k into x of or we can say v1 of k, where then you can substitute x of n and can find the further versions. Okay, Now from here we can say that if I take the z transform of this, then v of z will be equal to h of z into x of z raised to I. Okay, z raised to I, because we are doing the interpolation here. Okay, and that we know that it will be let's say if I convert it to omega, okay, and I put some demi variable omega v. Okay, we say that up till here the omega we get is omega v, and here I am going to get omega y. Then that's not a problem. I'm just introducing a dummy variable. So v of omega v will be equal to h of omega v into x of omega v into I. Correct? And we know that the transfer function of h of omega v is not constant everywhere. It's a low pass filter, and the characteristics of that low pass filter is therefore we can write v of omega v is equal to I x of omega vi, okay, for 0 less than equal to mod omega less than equal to minimum value of either pi by d or pi by I, okay, and it's 0 otherwise. This is the output at the filter. So we got the output at the filter in the frequency domain as this. Okay, now what I do is I further decimate the next stage is we are putting this v of n at the input of the decimator. So y of z, that is a decimator which we are going to obtain at y of omega y, is nothing but 1 over d, okay, summation, okay, k goes from 0 to d minus 1, okay, v of omega y minus 2 pi k by d. Correct? And what is omega y by and v is not constant everywhere. So v exists only in this region of omega. So if I substitute that, we are going to obtain y of omega y, which is equal to, okay, 1 over d x of omega y over d, and is 0 otherwise, and this will be valid only for the minimum range of pi or pi d over I, and 0 otherwise. No need to prove this, because what does this show is what we have done is we have filtered it carefully and there is no aliasing. So for that reason we are keeping k is equal to 0, because there is no shifting and there is no aliasing, and once we filter it out we will get only one set of information. So for that I am putting k is equal to 0. When is k is equal to 0, I will get omega y by d. So omega y by d, because there is no and the transfer function of the filter, we are assuming it to be 1 in that case, so it will give me sorry, not 1, it's I, so it will be I over d. So it will be I over d x of omega y by d. So it is nothing but a downsampled version of x of 1 and also interpolated by I. So it will be I over d omega y by d. So this is the characteristics of a sampling rate converters with a rational factor. Okay, so whenever they ask you to explain or describe sampling rate converter, you will draw the basic functionality of how to cascade the system and why to cascade the system. Then once you cascade the system, how the filters are operating at same rate, and because they are operating at same rate, you can combine the filters and make one filter. And once you make it one filter, then you have to give its characteristics as what it will be, and then you can show that what will be the output at what will be the output at particular stages, like output after filter and then output after the downsampler, and the final value of output should be like this. So this is what the complete information about sampling rate converters. Thank you.